All right, so here we have to use the integral test and determine convergence. But there are some conditions. So we need to make sure that the function within the series is positive, decreasing, and continuous. Positive in the sense that is on the upper right-hand side of a graph, which 3 to the negative n is. So it's positive. And decreasing would mean that each term in the series is getting smaller, or basically that the graph itself is just on a downward slope like that. Eventually, it can start like that, but as long as it eventually decreases, that will work. That is also true. And continuous. This is always continuous. There is no term in which it is not working. Therefore, we can use the test. So you're supposed to take the limit of the integral, and if you get a constant, then it works. So I'm going to use a little workaround and just cheat around the limit by immediately putting in infinity. So just focus on integrating for now. This is a standard integral. You're going to want to put your term to terms of e and then use u substitution. Pretty simple so far. Don't forget to adjust for your new values on the closed interval. Of course, when you plug in infinity into n, you're going to get negative infinity, so that's important. And that means that negative ln3, when you plug in n for 1, is going to be a bigger value. So the bounds flip, which also means that this is going to yield a negative sign. And because the constant from our du is already negative, then we can just cancel out right here. You can then take that, pretty easy, since the integral of e to the u is just e to the u. And then, of course, oops, didn't mean to do that. Just take the limit now. So this is pretty simple, although it doesn't look simple because of the way I've written it. Just understand that this means that e is really ignore that 1 over right here, right? That's the exponent. And the same goes for this right here. It's 1 over e to the infinity. And you just have to find the limit of this. And the limit of e to the infinity power is 0, which cancels this out, which means the only term we have left now is what we have right here, which is basically boom, 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 yes, this right here. And where did the 3 come from? Just think of e to the ln3 as the same thing that we switched out for standard value for 3. So this is your final value. It is a constant. Therefore, everything converges. So we need to use the integral test again to determine the convergence or divergence of the series. And of course, they have prerequisites. Is it decreasing? Of course it is, because n is in the bottom, and it will continue to be smaller and smaller as n increases. Is it positive? There are no negative signs. And is it continuous? Well, because n starts at 2, yes it is. Let's see. What you want to do is set up your integral. Obviously, that's what it's going to look like. You can see we have a pretty sweet u sub waiting for us right here. You can use log n, and then the 1 over n disappears. Don't forget to fill in your new interval. Pretty easy stuff going on. And then you got your new integral and its product. I don't know if that's the right terminology, but here's what we got. And then, of course, you need to take the limit of this. So that is exactly what I have written down right here. And you can see that as you take the limit of this thingy right here, it's not too pretty. This goes to infinity, which automatically means that the answer goes to the limit, heads to infinity, and it diverges. All right, so for this question, we need to determine the convergence divergence again. We don't have to use the integral test, but we can use the P series as I've written out. If you look at the series we've been given, there is an n value and an exponent value, and that's all we want to look at. Just ignore the constant 3 up top. The question is this right here greater than or less than 1? Because if it is greater than 1, the exponent I mean, then the series converges, as I've written down. But as you can see, 2/3 is less than 1. Therefore, the series diverges. All right, so here we have to determine the convergence or divergence of the series. I'm not going to say that, but we can figure out the prerequisites to the integral test, which we have to use. So it is obviously decreasing. The n values on the bottom. Is it positive? It will be in the top right corner. So yes. Is it continuous? Yes. The starting n value is 2, so everything checks out. Let's put it into the integral right here. Have a pretty easy u substitution. Just take ln of n. You get rid of that 1 over n, which is convenient. Don't forget your bounds of integration. Important stuff right there. Now we move on to integrating. Once again, very, very easy, simple stuff. Go along the line, do it. And here is where we take the limit of the end result of our integral. So you can see as the limit of 1 over negative infinity, that's just going to head right towards 0. So this is looking pretty good for convergence. Then, of course, the limit of ln2 is just ln2. So here's the limit. Because it's a finite number, it converges. All right, we are to use the comparison test to determine the convergence of this lovely looking series here. And we have a couple things to cover. One, the comparison test, or at least the limit comparison test, says that if we have this series right here, then if we have something else like related to it, like 1 over n, and then we take the limit of that series on top of the other one, and what we get is something that is like a is greater than 0. That means that they either both converge or both diverge according to the other one that we picked. So we just want a to be bigger than 0 and finite. All right, so with that being said, boom, that's what we get. Use L'Hopital's rule. Very simple thing to do. You get 1 over 5. It diverges. Why does it diverge? Because 1 over n, the value that we picked, well, because of the p-series, it has a 1 right there. And for the p-series to work, you have to have this exponent be bigger. It has to be bigger than 1. And it's not. So it diverges. Diverge. Right here, we have to use the limit comparison test to determine the convergence or divergence of the series. We will pick 1 over n for our other factor in this limit comparison test. And you can see, as we do L'Hopital's rule, it'll be like a n squared over n squared situation. And of course, there's a plus 1, but that is just fine. This turns out to be 1, which is greater than 0, which means that they either both converge and diverge according to the thing that we picked. And 1 over n diverges, therefore this series diverges. Alright, in this problem we have to use a limit comparison test to determine the convergence of the series. For my comparison function, I've chosen 1 over 4n because that converges per the geometric series, because the term in the middle is less than 1. Now when we put that into our limit, you're going to get this. So what we can do is separate the 4 to the n power in the denominator, so we can then factor out 4 to the n from the denominator. And what you can see here is that we can cancel. And at this point, our limit is a lot easier to take. So when you look at our new function, when this n tends to infinity, this little fraction becomes 0. So what you have is 5 over 1. And then, of course, the limit of 5 over 1 is just 5. And, of course, the limit comparison test says that if you get any finite number that's bigger than 0, then both series either converge or diverge. Since this converges, then our original series is going to converge. All right, here we have to find the convergence or divergence of the series tangent 1 over n. I've decided to use the limit comparison test, and the function I'm using to compare to tangent 1 over n is 1 over n itself, which diverges per the p-series, where the exponent there needs to be bigger than 1. It happens to equal 1, therefore it diverges. So I'm going to throw it into our limit. And you're just going to take the derivative of the numerator and the denominator individually. Don't be tempted to put the 1 over n in the numerator. You're going to get this, and you'll notice that you can now cancel the numerator and denominator, and then rewrite your limit. Now, as n tends to infinity, this is going to be 0. So what you really have here is secant squared 0. And if you rewrite that, it's just 1 over cosine squared 0. And what is cosine of 0? 1. What is 1 squared? 1. So after that, you're just going to put your answer right there. You get 1, and that would be the answer for your limit. The limit is equal to 1, which is greater than 0. So this matches the divergence of the series we get. Therefore, the series we initially worked with. All right, so for this alternating series, we need to use the alternating series test to determine convergence. We're going to first take a look at the series without the alternating factor up top and see if the limit as n tends toward infinity is equal to 0. And it does. This right here, this fraction, is going to be 0. All right, and the next thing, the sequence itself, an n equals 1 to infinity, needs to continuously be getting smaller and smaller numbers. And this goes hand in hand with the limit. As it tends to 0, every single number, as you go an plus 1, is going to be smaller than the previous. So it is decreasing, and the limit equals 0. And if those two terms check out, then an alternating series is convergent. So that means that this series right here. All right, so for this question, we need to figure out if it's conditionally convergent, absolutely, or diverges. And we can use direct comparison to figure it out. So you can see I've taken the absolute value of the series and put it next to the series 1 over n squared. And we know that 1 over n squared converges per the p-test. Now, what happens when these two values are the same? What is n in that case? Well, when n is equal to 4, they're equal. So if we take n to any value higher than 4, the 1 over n squared is going to be bigger than 1 over n factorial, which means we can use direct comparison, making our series an and b sub n respectively. And because b sub n is greater than a sub n when n is greater than 4, that means that this converges when n is greater than 4. Therefore, our original series converges absolutely. All right, so for this one, we need to figure out if it converges conditionally, absolutely, or diverges. And we can use the limit comparison test to figure that out. Now, I'm going to take the absolute value of our series right here. And using that value, I'm going to compare it to 1 over n squared, which converges per the p-test, or p-series. Now, when we take the limit, you can see that the degree in the numerator and the denominator are both 3. So it's going to come to a limit of 1, which is greater than 0. Therefore, these series share convergence. So if this series converges and that one converges, that means that this one is absolutely. All right, so we need to figure out if the series sine n over n squared is an alternating series and whether or not it converges conditionally, converges absolutely, or diverges. So what we can do to figure out if it's an alternating series is just put out the inequality of sine. So it's true that sine lies in between -1 and 1, but it doesn't necessarily have a pattern like, say, -1 to the n or -1 to the n plus 1. It's not so immediately negative or positive. So for that reason, it's not an alternating series. But what we can say in terms of convergence is the following. So we know that sine, or rather the absolute value of sine, is less than or equal to 1. And what if we now divide that by n squared? You'll see that this is looking like the direct comparison test. And we know that if this value converges, which it does, then a lesser value, aka this, sine n over n squared, will also converge. And since we're taking the absolute value, that means that it's going to converge absolutely. All right, so for this, we have to use the ratio test to determine the convergence of the series 3 to the n over n factorial. I've already set up the limit, and we can just start canceling out some stuff, starting with the 3n, also the n factorial, because this is just going to become n plus 1 n factorial, and then you get rid of that. So you're going to get 3 n plus 1. And if you take the limit as n tends to infinity, this is going to go straight to 0. And per the ratio test, anything less than 1, aka 0 in this case, is not just convergent, it is absolutely convergent. All right, so here we have to use the ratio test to determine the convergence of, or divergence of, the series n factorial over n to the n power. I've already set up our limit, so we can just start canceling. You can start with n plus 1 n factorial, and then cancel that denominator with the numerator. And then if you look right here, you can see that it's raised to the n and to the first power, which means the first can go away because we have one in the numerator. So now, take your limit as n tends to infinity of n over n plus 1, and they're both to the n power, so you can just throw that up in the top right hand corner. And if you take a closer look at this function, you can actually factor out the n from the denominator, and that becomes 1 over n. Of course, everything to the n. And once you come here, and you take the limit, as n tends toward infinity, of course, these are going to go away. So you're going to have this over n. And you can take a step back and realize that this right here is actually equal to 1 over e. Because when you take this n and throw it down here, that's now the value of e. And 1 over e is less than 1, therefore this series converges. All right, so for this, we have to use the root test. And the root test says that for any series a sub n, if you take its absolute value and put it to the 1 over n power, which is equivalent to just throwing a radical like that, if the limit of that is, if the limit is less than 1, it converges. If the limit is greater than 1, it diverges, and if it's equal, then it is not inconclusive. So, that being said, let's take a look at this series. I ran it down, and conveniently, if you take it to the 1 over n power, these two are going to cancel. So now, all you have to do is L'Hopital's rule. And when you do L'Hopital's rule, you're going to find that the limit is equal to 2. And 2 is greater than 1, therefore, this series is going to diverge. All right, we have to determine the convergence or divergence of the series. And 7 to the nth over n factorial. I'm going to use the ratio test I've already written down. Let's just start canceling stuff. So first thing we can do is get rid of the 7 to the n. Then we can break this down into n plus 1 n factorial and get rid of a couple things. First of all, this n factorial can go, and then this n plus 1 in the numerator can go. So now all we're left with is 7 over n. And if you take in the limit of that, as n tends toward infinity, you're going to get the limit is equal to 0. And 0 is less than 1, therefore this limit is going to converge.